have a balloon here. I'm going to blow it up. I want a large surface area. Here, near an air vent, I'm going to stick this balloon to the ceiling. Now, in the air, alongside the oxygen and the nitrogen, the carbon dioxide, the water vapour and the argon, there's a very small amount of radon. The radon that was produced underground that has come through the floor and is in the air that we breathe. Now, in enclosed space, like the air conditioning units, that radon could actually build up, not able to vent into the wider atmosphere. And here at an air vent, you might find there's a slightly greater concentration coming out. Now, that radon is continually decaying with a 55-second half-life into polonium and radioactive isotopes of lead. Now, what we're going to try to do here is we're going to see if we can detect any of those daughter products of the radon decay chain on this balloon. So we're going to leave this here for about half an hour, and then we're going to come back and look at it with a Geiger counter. To make sure this experiment is valid, I've blown up a second balloon that I'm going to leave in the room for the same amount of time as the one that's left in the airflow. At the end, I'm going to use this large aperture radiation detector to measure the radiation coming off both balloons. If I'm right, what will happen is that we should get more radiation from the balloon that's in the airflow. The concentrated radon that has got trapped in that space blowing out onto the balloon is not going to stick to the balloon, but the daughter products of the radon, the polonium and the lead, will do because their chemistry is different. And so what we hope to see is that in the airflow is going to be more radioactive because it has more of those daughter products from the radon decay on it. The decay of radon from radon to polonium can be written out in a nuclear equation. Look what's happening here. The radon is by itself. It's not a chemical reaction where things are mixing. It's just spontaneously decaying. This decay is indicated by the arrow here, producing two products. There is a daughter product, which is a new isotope of a different element, and there is the alpha particle here. Look at how the numbers are conserved. Here, the mass number 220 is turning into 216 and 4, which is still 220. No protons and neutrons have disappeared in this process. We need the same mass in total on the right-hand side as on the left. Also look at the atomic number. 86 here and 84 and 2 here. 84 plus 2 gives 86. So we've preserved in this alpha decay the total number of protons. Now, these decay equations are really powerful because we can use them to make predictions about what might be produced if something underwent a decay. This polonium does not hang around very long. It very quickly turns into something else. And it does this through the emission of another alpha particle. So the first thing we can do is we can put in an alpha particle. Now, the alpha particle isn't subject to change. It's always 4 at the top and 2 at the bottom. But it enables us to make a prediction about what we might get off as a daughter product here from the polonium decay. So what we see is that if 4 of the protons and neutrons have gone with the alpha particle, then this number is going to decrease by 4. So the mass number is going to go down to 212. Here, the atomic number is going to go down by 2. So 84 minus 2 is 82. But this is a new element. In fact, if we look at 82 on the periodic table, it turns out to be lead. Radioactive isotope of lead, lead 212. This is an alpha decay. The beta decay and the gamma decay is going to look different, but the principal fact that these nuclear equations can be used to predict what either the daughter products are or the emitted particle is very powerful, and we're going to use it. So let's go with our control balloon to start with. And what I'm going to do is I'm going to slowly let the air out because what I want is, I basically want to concentrate the surface down to a smaller area so that I stand a better chance of detecting anything. So here we go, I've completely deflated it. I'm going to set the counter running, get an incident. Here we go, it is now counting, and I'm going to place my balloon on the detector and start the stopwatch. Now I'm going to leave it for an integration of 2 minutes to see how much radiation is coming from that balloon. Two minutes. 371 counts from the control balloon. Now let's try it with the balloon that's in the airflow. 2, 1. There we have it. 895. That's almost a factor of 2. So what we can see is that with the blue balloon, 371, with the pink balloon put in the airflow, nearly double that amount. It has been picking up the polonium and the lead atoms that were created by the decay of radon. And so therefore our predictions that the decay of radon would not produce a noble gas but produce something that was capable of sticking to a balloon has been validated. So now I'm going to have a look at this beta source. It says strontium-90 on the box. I'm just going to bring it close to my detector. And you can see there are definitely beta particles coming off it. So the question is, can we use nuclear equations to predict what the strontium-90 is turning into? To understand the nuclear equation for a beta decay, we must understand what's happening in the nucleus to produce a beta particle. What is happening is a neutron, which I'm going to call 1, 0, because remember this number at the top, the mass number counts the number of protons and neutrons, and there is a neutron here. The atomic number down at the bottom counts the number of protons, and there is no proton here, it's just a neutron. A neutron is decaying into a proton. Now a proton, it has a mass number of 1 because there is a, the mass number counts the number of protons and neutrons, and there is a proton here, and the atomic number is a 1 as well. Now what is given off, in order for the neutron to become positively charged, it has to get rid of some negative charge. So it gets rid of the beta particle. Now the beta particle has no mass, but it does have a charge of -1 because it's an electron. What you can see is that this is consistent, that the mass number, 1, 1, it's equal to 1 on both sides. It's also consistent with the atomic number, 0, and 1 and -1 is equal to 0. It stays 0. So let's have a look at the strontium-90. So strontium-90 is Sr9038. What's going to happen when it gives off a beta particle? Well, let's draw the beta particle in first. So the beta particle is 0 and -1. So we know that the products of this decay is going to have a mass number of 90 still, because it has to equal 90 on both sides. So what number, -1, equals 38? It's actually 39. And so the products, and I think that's iridium, but let me check. Not iridium, it turns out it's yttrium. Shows how much I know about chemistry. Yeah, element 39, what's actually happened is, and this is what people find most difficult to understand, is that by the emission of the beta particle, we've actually gone to a heavier element. The actual isotope itself is not heavier, the actual mass is the same. It's just one of those neutrons has turned into a proton, and so therefore it has to move along 1 in the periodic table. But notice how for the beta decay, it increases in atomic number by 1, and in the alpha decay, it decreases in atomic number by 2. What happens for a gamma decay? Well, a gamma decay changes nothing. Say, for example, we had U238, 92, undergoing a gamma decay. Well, if you remember the notation for gamma decay, it's 0 mass, and it has 0 number of protons, then it's not going to change the uranium at all. It is just going to remove some energy from it. So we don't expect with a gamma decay to see any change in the element. But with a beta decay, it goes to 1 proton more. With an alpha decay, it goes 2 protons less.